Chemical elements like carbon, nitrogen, oxygen combine to form larger compounds, which are then used to build tissues, organs, organ systems. Knowledge of these chemicals, how they behave, can help us to understand the scientific basis of life because it helps us anticipate how chemical reactions will occur, what things bond together, and the utility and functionality of them within the living system. We begin with the atom. That an atom is composed of 3 subatomic particles. Be aware of the proton, neutron, and electron. Recognize their names and the charges associated with them. Oftentimes in science, you can break down a word to understand its meaning and its root relationships. So proton, that pro is a prefix for positive. Neutron sounds a lot like neutral. That tells us it has no charge. Electron, think electricity, and getting hit with that would be a bad thing. So that's a negative charge associated with it. When these subatomic particles come together, the protons and the neutrons form the nucleus of the atom, and the electrons dance around in a cloud that's very far away from the nucleus. So there's 3-dimensional shape, and these electrons are constantly moving and in flux. They're the ones that are engaging with bond making and bond breaking. A couple of trends that we see is that the larger the atom, the more particles it's going to have in the nucleus to stabilize it. And to keep the element balanced, the larger the nucleus, the more protons it has, the more electrons it will have orbiting to balance the charge. Activity refers to its willingness to participate in reactions, how energetically seeking or stable it is. If something is stable, it means that it's not reactive. It will not participate in bonds because it doesn't need to. If it is highly energetic and unstable, it will be very reactive because it's seeking an extra electron to find that balance. And so we can see as we go across the periodic table, far on the right are the noble gases highlighted in red. They have a complete octet of electrons in their farthest orbital, meaning that they are very well balanced. There's little to no reactivity, and so they do not engage in chemical reactions without excessive energy being applied. The atom itself is organized kind of like an onion in layers upon layers where electrons can orbit in their own plane. We call them orbitals. The idea here is to minimize traffic jams and crashes because they are highly energized molecules. The octet rule states that if there are 8 electrons in the outermost shell, then this element is stable, and that elements will combine and participate in reactions seeking that final 8th electron to where they would find themselves balanced, stable, and no longer reactive. Reading the periodic table can be tricky because it's composed of letters and numbers. First thing to know is that the elements are all arranged by their size in columns and rows. We call the columns groups and the rows periods. The groups are all organized based upon shared characteristics. Generally speaking, it's looking at how many valence electrons there are in that outermost shell, because that tells you how reactive this grouping is going to be and willing to participate in reactions. The period will reveal information as to how many different electron orbital shells that element has to organize it. The first periodic table was written in 1869, and at the time we only had 64 elements. Today there are roughly 118 elements. 92 of those are naturally occurring components found in the earth. The others have been man-made. If we were to zoom in on a single element in this table, we could gain further insight about the behavior of that element. In the top center or the top left, is where you'll find the atomic number. The atomic number is unique to every element, and it reveals the number of protons, just protons. At the bottom of the element square is a number that may or may not be a whole number, the atomic weight. The atomic weight is an average of the total number of particles in the atom's nucleus in all its naturally occurring forms that exist. If you were to round this up to a whole number, this reveals the mass number, and it's both protons and neutrons. So looking at the atomic weight, we can see that it's close to the mass number, but it's not exact. How could something be 0.8 of a proton or neutron? Well, again, the atomic weight is an average of the different forms that exist, and these different forms are called isotopes. Neutrons, because they offer no charge, are not restricted in the same capacity as the protons and electrons of an element. The number of neutrons is therefore independent of the atomic number. You could add neutrons or delete neutrons, and it wouldn't affect the element's constitution, although it might affect its stability. And so what we're seeing here is isotopes of carbon. In all three cases, there are 6 protons and 6 electrons, 6 positives, 6 negatives, a very well-balanced charge of this element. But in each of the 3 examples, we see the neutrons vary from 6 neutrons to 7 neutrons to 8 neutrons. And so when we add 12, 13, and 14, the numbers of the protons plus neutrons, and then divide that by 3, that gives us the atomic weight of carbon, an average of its various forms. What I've pointed out in the star is the naturally occurring way that we find carbon, the most common way that we find carbon. And I made note that it's non-radioactive carbon. One of the isotopes, carbon-13, is also non-radioactive because adding just 1 neutron in there doesn't throw things off much. But carbon-14 is radioactive. And what that means is that its nucleus is now unstable and will release energy. This means that radioactive carbon is more likely to engage in a chemical reaction. That doesn't mean that it's Chernobyl waiting to happen. What that means is that it will exhibit functional changes much more readily. So how do we put these elements together to build life? All matter, desk, trees, human, animal, are composed of tiny atoms, many, many atoms. When we combine any 2 atoms, we get a molecule. A molecule can be 2 atoms big, a molecule could be 27 atoms big. If that molecule is all composed of the same type of atom, only one kind of atom, if it is pure, we call it an element. If the molecule is mixed of different things, we call it a compound. Be aware of this terminology. Everything that matters exists in one of 3 physical states: solid, liquid, or gas. Matter is defined as being composed of elements that occupies both space and has weight. But how they exhibit this space and mass varies depending upon the phase they exist in. So for example, solids have fixed-shaped, fixed volumes. Liquids, the shape varies depending upon the container it's in, but the volume stays the same unless you spill it. And gases are both variable in shape and space. An interesting thing to note is water is the only compound that exists in all 3 states naturally. It takes 60 different elements to build the human body. Many of these are present, and we don't know what they do. but 25 of them have been described as essential. What does that mean? Well, to be considered essential, we have to A, know exactly what it does. B, know that it is the only thing that does that task. There are no replacements, there are no substitutions. And C, we know that without it equals death. So what holds them together? Chemical bonds. Ionic bonds, ions, are formed when electrons are transferred from one atom to another. The ions are attached to those temporary positive and negative attractions between charges. So in this story that we have here, the sodium atom, Na, is passing an electron to the chlorine atom. So the sodium becomes less negative, slightly positive, and the chlorine atom becomes slightly more negative, having gained an extra electron. And it is during this time, this temporary transfer, passing of an electron, if you will, that these two atoms are bonded together. Covalent bonds are much more long-term. They are formed when electrons are consistently shared between atoms. And so their electron shells overlap and both atoms are holding onto the electrons. Covalent bonds can be described as polar or nonpolar depending upon how well they share those electrons. Polar bonds occur when there's uneven sharing of electrons, when one atom is holding on to more electrons or holding the electrons closer to its nucleus. Nonpolar covalent bonds are those that have equal sharing. And so you can see that depicted in the bottom, where the cloud around the carbon is much bigger than the cloud around the hydrogen. So that's a polar covalent bond. But in the carbon-carbon relationship, they're equally strong. And so it's the well-balanced tug-of-war of those electrons, and it is a non-polar bond. The more electrons that are shared in these covalent bonds are what builds double or triple bonds. I also want to point out weak forces, hydrogen bonds and van der Waals interactions. Hydrogen bonds are formed when the partial positive charge of the hydrogen specifically is attracted to any electronegative atom. And van der Waals interactions are similar, but it's occurring between any other slightly positive, slightly negative molecule. These relationships, because electrons move so frequently and quickly, are very fleeting. As we move forward and build upon our understanding of chemistry, let's talk about how we read a chemical reaction. We need to break things down. All the letters are element abbreviations. Some of these are single letters, such as the C for carbon. Some of these are two letters, Fe for iron. The Fe is actually short for ferrous, the Latin name for iron. Subscript numbers, the numbers that hang low, refer to how many of the element before it. So C6 is saying that there are 6 carbons in this molecule. H12 is saying that same molecule has now 12 hydrogens. Superscripts, like this +3 or this minus, refer to charge, and they come after the element. And so we can see here that iron, Fe +3, has a positive charge of 3. There are 3 more protons than electrons here. And that the chloride ion, Cl, is only -1, 1 more electron than proton. And if you see a large number, as in the case of this 2 preceding the compound, it's referring to how many units of that type of compound do you have. So 2 C6H12O6s is actually saying that there are 2 glucose molecules here. That means there's 2 times the number of carbons, 2 times the number of hydrogens. So all in all, if we were to put 2 C6H12O6s into a beaker, we would have 12 carbons, 24 hydrogens, 12 oxygens present. All chemical reactions involve bond breaking and bond formation to change the composition of matter, to change how it's organized and structured, as well as its properties. When reading a chemical equation or a chemical reaction, we're looking for specific terms. The reactants are the starting material that's participating, reacting in this experiment. The products are what we're producing at the end result. The substrate refers to where this is taking place. And we read chemistry like we read English, starting from left to right. So on the left of the arrow is the beginning, and on the right of the arrow is where we're ending. You might also see terms like solvent and solute. The solvent, the V, kind of looks like a cup. This is referring to the liquid in which things dissolve. The solute is whatever solid or gas is dissolved and carried inside that liquid. There are many types of chemical reactions that can take place when you're breaking and making bonds, but ultimately they distill down to 4 basic changes. Be aware of these 4: the synthesis, decomposition, single replacement, and double replacement reactions. In synthesis, we're taking small things and combining them to make a new, bigger thing. In decomposition, we're doing the reverse. We take a big molecule and break it apart into smaller components. In the single replacement, we are swapping out just one element for another. So this involves both bond breaking and bond making. In a double replacement, 2 elements will trade partners. And these reactions will tend to occur until chemical equilibrium is met. So be aware of what that means, equilibrium. It means that reactions are still technically going and occurring because life doesn't stop on a dime, but that the reactions of building things and breaking things, the forward and reverse reactions, are proceeding at equal rates. So there's no net change. There's a balance in there. Composed of hydrogen and oxygen. Water is life. All life is made up of mostly water. The human body is about 70% water. Jellyfish are about 90% water. All organisms require water. Why? Because water is both a temperature stabilizer as well as the universal solvent. So water is able to dissolve almost everything. And so we need water to constitute our cells, to provide a floating space in which elements can move and dissolve in and participate within chemical reactions. It's also protective and cushioning and moderating for the organism. Some unique features of water that make it so irreplaceable. It is the most polar substance on the planet, meaning it has the most uneven sharing of electrons. There's a very huge electron cloud around oxygen, which alters the physical shape of the water molecule, creating a side that's very negative and a side that's very positive. And this creates those temporary dipoles, those temporary reactions between charges. We referred to them earlier as hydrogen bonding. At this point, I want to expand on that and recognize that there's cohesion and adhesion. Cohesion describes attractions between molecules of the same substance. So it's hydrogen bonding between water and water. The root here is cohesive, right? All of one mind. Adhesion is when it's a hydrogen reaction between another molecule. So water and something else, because other things may be bonded to hydrogens as well. But the hydrogen bonding that exists between water can give rise to some really interesting phenomena, such as surface tension, the ability of that water droplet to retain its shape. The hydrogen bonds between those water molecules are holding it cohesively together because multiple hydrogen bonds can form given there's multiple hydrogens in each water molecule. So when we say something has high surface tension, we're describing how much pressure needs to be exerted to break the surface of a liquid. Hydrogen atoms are some of the most reactive atoms in the periodic table because they're furthest away from being a noble gas. They only have 1 electron in their outermost shell. And so they're constantly seeking other molecules to bind to and react with. And so hydrogen atoms themselves can sometimes jump ship from one water molecule to another, creating temporary H3O, hydronium ions, or OH, hydroxyl ions. These forms explain acids and bases. Acids are those solutions in which there's more hydrogen ions in solution, and bases describe solutions that have more hydroxyl ions in solution. Buffers are those solutions that can either donate hydrogens or hydroxyls as needed to help balance things and minimize the changes accumulating within that solution. So when we look at the acid-base spectrum, we create a scale of pH, parts of hydrogen. It goes from 0 to 14. Numbers 0 through 6 describe the H+ solutions. The 8 to 14 describe the OH solutions. And right in the center, with a pH of 7, what we consider neutrality, neutral, is water, because it is both one H and one OH.